Buenas noches! Our subject tonight is analytical geometry without linear algebra. Let's begin with baby Euclidean algebra. Proposition 1. On the plane over a straight line, describe an equilateral triangle. Euclidean hypothesis 1. For each pair of distinct points passes one and only one straight line. Axiom 2. Each straight line contains at least 2 points. A3. There exist at least 3 distinct non-collinear points. A4. The distance from P to Q is greater than or equal to 0 for all PQ in the Euclidean plane. The distance from P to Q is 0 if and only if P is equal to Q. The distance from P to Q is equal to the distance from Q to P for all P and Q in the Euclidean plane. For each Euclidean plane in the Euclidean space. We claim that let AB be distinct points given defining the segment AB such that the distance from A to B is R, equal to R, the radius. 2. Letting E be the Euclidean point, we define the circumference or circle of center O and radius R as the geometric place of the points of the plane which are at a distance R from O, IA, circle, center R, radius, center O, radius R is equal to the points X in E such that distance from O to X is equal to R. 3. We write and draw CA, R, CB, R. 4. These two circles meet in 2 points, at 2 points, CA inter CB equals to P1, P2. Do you believe they meet at 2 points? We will show. At other geometries, they do not meet always in 2 points. We will use analytical geometry and Pythagoras theorem. A5. Each line L in E has some coordinate system which is a bijective function f such that f is defined from L to R. The distance from P to Q is equal to the distance from f of P minus f of Q for all P, for all Q in the straight line L. Therefore, I might call the only single line, straight line AB of X edge, its coordinate x coordinate A equals to at A is equal to 0, its x coordinate at B is equal to big R. A6, the set of the E points which do not belong at a given line L, they are, the set is a reunion of two disjoint convex sets. They're called semiplanes, half planes, such that if P is in one of them and if Q is in the other one, then the segment PQ intersects L. A7. To each angle ABC, it is associated a single and only number m from ABC to which we call the amplitude of the angle, the measure of the angle. And this number is in the interval, open interval, 0, 180 degrees. Different from 0, different from 180. Let A and B be two distinct points. Let H be one of the half planes determined by the straight line AB. So, therefore, given alpha in the interval 0, 180, there is one only and single semi-half straight line AP. P is in H, and measure of the angle PAB is equal to alpha. Therefore, I can call of y edge, the edge y, the only and single straight line AP perpendicular to AB. And each point of the plane is uniquely represented by an ordered pair x and y. Let's prove Pythagoras theorem. A9. D is a point inner BAC, the angle. Then the measure of the angle BAC is equal to the measure of the angle BAD plus the measure of the angle DAC. A10. If ABC and ABD, if they are adjacent, supplementary, i.e., if B, C, and D are collinear, the same straight line, and if B is intermediate to C and D, CBD, then the measure of ABC plus measure of ABD is 180. A11, the best, no, not the best, the last minus one. So 12 axioms. If in a correspondence between two triangles, two sides of a triangle, and the angle of them, if they are congruent of the correspondent parts of the other triangle, then this correspondence is a congruence, i.e., better in symbols. If the distance from A to B is the distance from D to A, if the distance from A to C is equal to the distance from D to F, if the angle CAB is the angle FDA, then the two triangles ABC, triangle DEF are congruent. Continuing the reasoning, let ABC be positive numbers. Let the points be big A 0, 0, B A 0 greater than 0, C A plus B 0 in the plane. D A plus B A, E A plus B A plus B, F B A plus B, G 0 A plus B, H 0 B. Then from the axiom 11, these four triangles are congruent. The triangle BAH, the triangle DCB, the triangle EFED, and the triangle HGF. They are right triangles. The cathets are A and B, and the hypotenuse is C. A12. For each external point to a given straight line L passes at maximum as one straight line which does not intersect L. So there are elliptical geometries, there are hyperbolic geometries, and this is the Euclidean axiom, the axiom of the parallel. There is one only single line. From this axiom, we can state that the sum of the angles of a triangle, any triangle, is 180 degrees. Let's show. DBC plus BCD plus CDB is 108. Then ABH plus DBC is 90. BCD is 90. Well, ABD plus DBC plus HBD is 180. So HBD is 90 degrees. Therefore, BDFH is a square whose side is C. By the areas, the surfaces are triangles. The surface of a CAAG is equal to the surface of BDFH plus 4 surfaces of BAH. Here is a square of A plus B. Here is the square of C. And 4 multiplied by a right triangle. Catet times catet divided by 2. It's proven that A2 plus B2 is equal to C2. It's algebra. A2 plus 2AB plus B2 is equal to C2 plus 2AB. Therefore, the distance in analytical geometry between 2 points is the distance from xy to AB is equal to C if and only if x minus a squared plus y minus b squared is equal to C2. Now we have two circles CA and CB. The equation of CAR is x2 plus y2 equals to R2. The equation of CBR is x minus r squared plus y squared is equal to r squared. So we have a system. x2 minus 2xr plus r2 plus y2 is equal to r2. Subtract the equation 2 from the equation 3. It will remain 2rx minus r2 equals to 0. Our radius is greater than 0. So we must divide, and we might divide by a number different from 0, and by linear equation of first degree, 2x equals to r, x equals to r divided by 2. 2 implies that y is plus or minus square root of r2 minus x2, and x2 is r2 over 4. You do 4/4 minus 1/4, 3/4 square root of 3 over 2 plus or minus p1, p2. 1 for plus and 1 for minus. 5 for a single p. For any p between them, p1, p2, AP is equal to AB is equal to AP is equal to BP equals to R. Therefore, the desired equilateral triangle is ABP. We have constructed two equilateral triangles. Indeed, it is a rhombus. I used this book, Curso de Geometria, Geometry Course, Paulo Ventura Araújo, Editora Gradiva, Lisboa, 1998. Now we're going to the space. In the space we have a tetrahedron and a sphere. A polyhedra of 4 faces. It has a circunscribed sphere. And we put 3 axes, 3 edges, x, y, and z. We put our triangle in a way that A is 0, 0, 0, B is C, 0, 0, and C is greater than 0. It's possible. Then we choose the coordinates of C. P key 0, where P and key is greater than 0. That's possible. Then we choose RST, the coordinates of D, with T is greater than 0. We must have T greater than 0 as hypothesis. This gives A, B, C, D a polyhedra. The center of the circunscribed sphere is X. Its coordinates are X, Y, Z. X is C over 2, Y is P2 plus Q2 minus CP over 2Q, and Z is Q, R2 plus S2 plus T2 plus S, CP minus P2 minus Q2 minus CQR over 2QT. The distance from A to X is C2 over 4 plus Y2 plus Z2 equals to R2. Bx2 is equal to R2 is equal to Cx2 is equal to Dx2. X is equidistant from 4 points. From distance from A to X is equal from the distance from A, B to X, distance from X to C, distance from X to D. The same triangle ABCD has an inscribed sphere with an area with a radius and a center. The center coordinates are X, Y, and Z now. If alpha is the plane ABC, the equation of the plane is Z equals to 0. The equation of the plane which passes from A, B, and D is Ty minus SC equals to 0. The equation of the plane gamma which passes from A, C, D is equal to QTX minus PTY plus PS minus QR Z equals to 0. It's easy to do that, and is an exercise. Delta is the plane BCD. QTX plus C minus PTY plus CQ minus QR minus plus P minus CSZ minus CQ2 equals to 0. Distance from point to plane. Distance from Y to P, where P is AX plus BY plus CZ plus D equals to 0. The formula is modulo of AX plus BY plus CZ plus D, the absolute value of this, over square root of A2 plus B2 plus C2. Therefore, the distance from Y to alpha is the Z itself greater than 0. The distance from Y to beta is the absolute value of Ty minus Sz over square root of S2 plus T2, we name it F1 greater than S. It's equal to Z. Z is alpha Y. So we're gonna isolate Y. ZF1 SZ divided by T, S plus or minus F1 over T. And we choose positive inclination at x equal to 0. I will choose plus. Don't worry, it will be explained. Y gamma is equal to, using the formula, absolute value of QTX minus PTY plus PS minus QR0 over square root of P2 plus Q2T2 plus PS minus QR2, which is greater than QR minus PS, one of the edges. Cathets. So here is distance equals to Z. Implies that we're gonna isolate Z. QTX minus PTY is equal to Z multiplied by PS minus QR, and we pass F2Z, so plus or minus F2, therefore X, we isolate X, not Z. X is QR minus plus PF1 plus or minus F2 over Q2 times Z. We have to use Y here. So we have QTX here, and we have PS Z here, and we have F1Z here times P. Delta Y, using the formula, the distance from a point to a plane is the absolute value of this thing over F3. F3 is square root of Q2 plus C minus P squared times T squared plus G squared, which is greater than G. Note that we're using the square root of the coefficients of the plane P. Note that here I chose minus F3, F2 on the contrary, because CQT is less than 0. This is the detail. I will not enter in details. Ending with who is Z. The distance from Y to delta is equal to Z, the distance from Y to alpha. QTX plus C minus P TY plus minus CQ2 is equal to Z minus G plus or minus F3. Oh my god. We only grouped Z. Now we're gonna isolate Z. Using X is a constant times Z and Y is a constant times Z. So KRZ, PF1Z, F2Z, C minus PT times SZ, F1Z minus CQ2 equals to Z times a thing. CQT over a thing multiplied by Z. Do the calculations. If G is CQ minus QR plus P minus C times S, and this G appears multiplying Z, and appears at the plane delta, CQ minus QR. Okay. We conclude who is Z? Plus F1 plus F2 plus F3. Y is Z over T S plus F1. S plus F1 over the same thing. X is KR plus F PF1 plus F2 over the same thing, multiplied by Z, which is CQ2, C, okay? Now, divided by Q2. Who is the point Y? The point Y is the center of the inscribed circle with coordinates x, y, and z. Coordinate x, QR, coordinate y, q, s plus f1, coordinate z, c, key 2. There was an exercise which I have done for congruent opposite faces. We now are going to suppose AB is equal to CD, AC is equal to BD, and AD is equal to BC. Who is D? RST. We conclude that doing the accounts, the point X is using that formula C over 2, P2 over 2Q, Q over 2Q2, coordinate X of X, coordinate Y of X, coordinate Z of X. And Y, there are 8 possibilities using these formulas. X, Y, and Z, CQ2. So here it is CQ2. And our sigma Y are 1 or plus or minus 1. Sigma 1 CF1, sigma 2 F2, sigma 3 F3. It's an integer number. F1 is equal to Q. Just calculate. F1 square root of S2 plus T2. We know who is S, we know who is T. We know who is F1. We know F2 is equal to CQ. We know F3 is equal to CQ. We know big Y is substituting F1, F2, and F3. This thing. Sigma 1 minus 1, PQ. Sigma 2 plus 1, CQ. U plus sigma 1, Q2. Square root of Q4 minus U2. From the 8 possibilities plus 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 2 minus minus minus, we calculate 1 plus sigma 1 minus sigma 2 minus sigma 3, and 1 plus 1 plus 1 minus minus 1 is 4. 2, 0, 0, minus 2, 4, 2, 2, 0. The 3 zeros belong to the empty set. Why? We are dividing by that sign. They are not convenient. We trash them out. 0, Z cannot be CTQ. Once 0, 0, Z cannot be CTQ, Y0 does not exist. There exists plus plus minus, plus plus plus, minus minus plus, minus plus minus, plus minus minus 5 points. And we're going to calculate. Calculating. Plus plus minus gives x. Plus 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 gives a point A line, which is 2x, where x is the same circunscribed sphere center as above. And we get D line, C line, B line, where X is the middle point of A and A line, X is the middle point of B and D line, X is the middle point of C and C line, X is the middle point of D and D line. It's a miracle. The numbers do not lie. We found 5 equidistant points of the faces of a regular tetrahedra. The regular tetrahedra 0, 0, 0, 1, 0, 0, a middle, square root of 3 over 2, 0, D, it's in the 1 half, square root of 3 over 6, square root of C over 3, ABCD is a regular tetrahedron. The center is the same, X and Y, 1 over 2, square root of 3 over 6, square root of 6 over 12, and A line is indicated, D line, C line, and B line, and here are written the equations of the plane alpha equals to ABC, the plane beta equals to ABD, the plane gamma equals to ACD, and the plane delta equals to BCD, which is AB plus CBY plus CZ plus D equals to 0 always, as you already know. Now we're gonna bisect an angle. Let 3 points be A, O, B. Let U be the vector A minus O over the distance from O to A. It's an unitary vector. A, O, O, B are points or vectors. V is a vector. B minus O plus over OB is a unitary vector too. We're going to name X the points. X are the points U that belongs to the plane AOB, such that the angle between U and X is equal to the angle between V and X. So it's a bisector plane. The points X are of the form O plus lambda U plus mi V, a plane such that the angle UX cosine scalar product, inner product of U times X minus O over modulo of U over norm of X is equal to the scalar product of V, this vector of X minus O, that vector over the norm of V times the norm of X. So we're gonna use that U minus V scalar lambda U plus mi V is equal to 0. Why 0? Because the left hand minus the right hand give us 0. This implies that lambda U times U minus V plus mi V U minus V is equal to 0. So UU 1, UV UV, VU minus UV minus VV 1. Divide, isolate mi lambda times 1 minus UV over 1 minus UV. Lambda is equal to mi. Therefore, X is O plus lambda U plus V. This is a line, a bisecting line. We're going to use that bisecting line to find the sphere tangent to the edges of a regular triangle. We know that A is 1, 0, 0, B is minus 1 half, square root of 3 over 2, 0, C is equal to minus 1 half, minus square root of 3 over 2, 0, and D is 0, 0, square root of 2. Distance from A to D is square root of 3. Distance from A to B, 2. Square root of 3. Let's determine the bisector of BAC. We let U be B minus A plus square root of 3, just like this, OA. We let B be C minus A over square root of 3. And X is O plus A plus lambda. Square root of 3 is 0, 0. S is a line whose points are x equal to lambda A. Because this vector is parallel to A. Now let T be the bisector of ABC. We let U be E minus B over square root of 3. We let V be C minus B over square root of 3. And the straight line T, whose points x are B plus lambda. Square root of 3 over 2 minus 3 over 2, 0. Simplifying, this straight line passes through the origin, and its director vector is 1 minus square root of 3 and 0. The intersection of the two lines S and ST is called O, 0. O is 0. Now we're going to determine the intersections of the sphere with the triangle ABC. We have three intersections, M, N, and P. M is in AB, N is in AC, P is in BC. M is A plus something times B minus A. N is A plus something C minus A. P is B plus lambda C minus B. OM is orthogonal or perpendicular to AB. M minus O times inner product with B minus A is equal to 0, orthogonal. A times B minus A plus lambda B minus A squared equals to 0. We isolate lambda. 3 over 2 over 3, 1 over 2. It's easy to multiply A by B minus A. M will be that point. Analogously, the same formula, lambda in this case is minus AC minus A over AC squared, and N is this point. Third case, lambda is minus B, C minus B over BC squared, also 1/2, and our point B is minus 1/2, 0, 0. Now we're gonna determine S2, the bisector line of DBC, the angle DBC. We let U be this vector, we let V be this vector, we let S2 be the points X given by the formula AOB X equals to B plus lambda U times U plus V. It is explicit. T2 is the bisector of BCD. U is one vector, V is another vector, T2 is a straight line, and it is explicit. Let I be the intersection of S2 with T2. This point is S2, here it is, T2, here it is, we exchange lambda by me, and we determine lambda and me by a system of 3 equations and 2 variables. You do that calculus, and lambda is equal to me is equal to square root of 3 over 3 by miracle. We found I, a point equidistant from S2 and T2. Now we're gonna use the intersection of the sphere with BD, the point Q in BD. IQ perpendicular to BD, the same reasoning. Q is B plus lambda D minus B, and Q minus I, inner product with D minus B is equal to 0. B minus I times D minus B plus lambda D minus B squared is equal to 0. Who is lambda? It's easy to calculate B minus I. Here is I. Here it is B. B minus I plus D minus B. Here is D, 0, 0 squared 2. Here is B. And 1/6, 1/2, 1/12 square of 3. Square root of 3 over 2. Square root of 3 over 2. 3 over 4. Minus square root of 3 minus square root of 2. 2/3. We do the calculations, and 1, 10, 18 over 12 divided by 3, right? 6 over 12, 1/2. Our point Q is equidistant from the edges, the 4 edges. Now, the sphere which passes from 4 points. M and PQ belongs to the sphere x minus a squared plus y minus b squared plus z minus c squared equals to R2. If and only if we're gonna isolate what? We're gonna put A, B, C, R one side and 2ax the other side, 2by the other side, 2cz the other side, x2, y2, z2 the other side. And using the coordinates above, x equals to 1/4, y equals to square root of 3 over 4, z equals to 0. Who is R2? The same for 1/4 minus square root of 3 over 4, 0. Who is R2? The same for minus 1/2, 0, 0. Who is R2? Do the calculus. And the fourth point, or 4 points, minus 1/4, square root of 3 over 4, square root of 2 over 2. Who is A2 plus B2 plus C2 minus 2R2? It's 1/2 square root of 3 over 2. By one side, we have this expression. By one equation, we have this expression. By the second point, we have this expression. By the third point, we have this expression. And by the fourth point, we have this expression. Doing all the calculations, you'll conclude that if the 4 is equal to the second, then we have an equation of first order degree of A and B. And 4 equals to 3. Another equation on A and B. Here is plus, here is minus. Then, therefore, 0 is alpha A plus beta B. 0 is alpha line A plus beta line B. 0 is 12A. A equals to B equals to 0. If 4 is equal to 5, then C is square root of 2 over 4. And if 1 is equal to 4, then who is our 2? Our 2 is 3/8. Square root of 3/8 is square root of 6 over 4. That's a subject of fundamental school, not high school. Now we're gonna do the calculations, the same calculations generically to the tangent to the edges. This will be harder to see. Let A be 0, 0, 0, B is C 0, 0, C greater than 0, C is picky 0, picky greater than 0, these are states greater than 0. Who is U? Is that thing. Who is V? Is that thing. And who is W? Is that thing. The same reasoning we did above, we determine the bisector of BAC using U, using V, if we know S. T is the bisector of ABC. We know U, we know V, we calculate T equals X equals to B plus lambda vector. We know I1 is the intersection of S and T. A1 is equal to B plus me times a vector. We have a system on lambda and mu. We conclude that A1 is that thing. So I1 is lambda vector equals to B plus me vector system and on lambda or me. Not new. We have already done this before with numbers. Now general numbers, variables, parameters. Let the computer calculate for you. Let us determine the intersections of the sphere with the triangle ABC, the points M, N, and P. M is in AB. M equals to lambda B. I1M is perpendicular to AB. M is that thing B. N is in AC. IN is perpendicular to AC. N is something that multiplies C. P is in BC. I1P perpendicular to BC. So, who is lambda? U lambda is equal to this. Lambda is a function of U. P is a function of U. And U, what is U? U is P minus C squared plus Q2. Let us determine the bisector S2 of DBC. We know who is U, we know who is V, we know who is S2, is B plus lambda vector. Let T2 be the bisector BCD, the angle BCD. U is this vector, V is this unitary vector, T2 is that line, I2 is the intersection of S2 and T2. So we have lambda and me, we have a system, lambda me is first degree. We know who is lambda, we know who is mu. I2 is a function of U, V, and W. The three coordinates, X, Y, and Z. T square root of U. And an identity because we have one coordinate, no, three coordinates and two variables. That's a miracle, no? Intersection of the sphere with BD, the straight line BD is a point Q. Q is in BD. I took Q is perpendicular to BD. Who is lambda? Q is a function of UVW. Who is M? Who is N? Who is P? That confusion. The computer knows it. I don't. M and PQ are in this sphere. X minus A squared plus y minus b squared plus z minus c squared equals to R2. If and only if 1 equals to 2 equals to 3 equals to 4. Again, equals to 5. Do you remember we have 5? 1, 2, 3, 4, 5. We have 4 points, 4 equalities, 5 members, 5 hands. So 2 is equal to 3. Who is A? 2 is equal to 4. Who is B? 2 is equal to 5. Who is C? And 1 is equal to 2. Who is R2? Quod erat demonstrandum. Geography. Geography is an exercise, difficult exercise on the end of the discipline spatial geometry in UFMG. My professor is not as frightened as you. The point A is 0, 0, latitude and longitude. The point B is latitude 60 degrees, longitude 60 degrees, and the point C is at the Earth. Any radius, the same radius, latitude lambda, longitude me, and they are equidistant. AB equals to C, AC equals to B, BC equals to A. By our known formula, the cosine of C is 1/4. The cosine of B is cosine of lambda, cosine of me. And the cosine of A is 1/2 cosine of lambda, cosine of me minus 60 degrees plus the square root of 3 over 2 sine of lambda. How do you become convinced of these formulas? You have to calculate the arcs. The length of an arc is proportional to the length of a circle, 2p radius. The length of an arc is proportional to the angle AOB. Comes from A, goes to the center O, goes to B. We multiply angle 2p by radius r. We have angle multiplied by radius equals to the length of arc. This is C, B, and A. Small c, small b, small a. By our high school formula, who is cosine of me minus 60? Cosine of me times cosine of 60 plus cosine of 60 times sine of 60 sine of me. Square root of 3 over 2 sine of me. Now AB is equal to EC is equal to BC. We have a system. 1/4 is equal to cos lambda cos me plus or minus. We name it this plus or minus by K1 is equal to plus or minus 1. And K2 is plus or minus cos lambda cos me 1/2 cos lambda cos me minus 60, which is 1/2 cos me plus square root of 3 sin me plus sin lambda. From this system, we have to find lambda and me. Who is me? The cosine of me is k1 over 4 cos lambda. The cosine squared is 1 minus sin squared. Sin squared is equal to that thing. Now, we let x be sin of lambda. And that equation 2 will become 60 x2 plus c dots equals to 0. It's a second degree polynomial equation. So use Bhaskara. Before Bhaskara, I will explain this. How we find that equation? We know who is me. We put me inside. It becomes only lambda. We only want sin of lambda. We don't want cosine of lambda. We have to square. Let sin 2 lambda equals to 1 minus cosine 2 of lambda. Then we eliminate cosine of lambda, and we have an equation and sin of lambda, which is x. Who is the delta of Bhaskara? It is that thing. The square root of the square of the coefficient of x minus 4 times the coefficient of x2 times the coefficient of 1, and sin lambda, which is x, is equal to the coefficient minus the coefficient of x plus or minus k3 square root of delta over 2a. 2 times 60, 120. Now, simplifying or unsimplifying, who is cosine of lambda? Square root of 1 minus the square of sin of lambda, plus or minus the square root of that thing. And who is the cosine of me? Where is me? Cosine of me is q1 over 4 cos lambda plus or minus 5 square root of 3 k1 over that thing. K1 is plus or minus, K2 is plus or minus, K3 is plus or minus. This gives to us sin of lambda and cosine of me. ABCD, DCBA, EFGH, HGFE. That's a miracle, no? So here are the answers for you. Agree. You can agree with me. You might disagree with me, but my calculus are A equals to this, B equals to this, C equals to this, D equals to this, and E, F, G, H equals to square root of 3 over 2 square root of 9, 2 minus 2 square root of 2. Out of charity, there is no salvation at all.